Hi, good morning, everybody. This is Bert. Please let me know in the chat if you can hear me well, or if you cannot hear me well. So today is the last class, really, aside, of course, from next week. Next week, we still have a probabilistic programming session and a bonus lesson on what is life. But for the regular, let's say, classes, today is the last one, and it's about agents. And agents are a bit different. I still haven't seen anybody saying anything in the chat yet that you can hear me. Can somebody just type something in the chat? Okay, good. So today, agents and agents are a bit different. Up till this point, we've talked about machine learning as if, and we always said, so I have a given data set, and now I want to build a machine that sort of summarizes that data set in a set of parameters. And then I use that machine to make predictions or do something else. But we always started with a given data set. And an agent is different. An agent is, yes, can do machine learning, but can also make actions onto the world. And if I can make actions, then I can actually change the dynamics in the world and thereby perhaps change the data that I receive. For instance, we ourselves, people, we are agents. If I look into a different direction, that's an action, I get a different signal on my retina. So by movements, I can change the data that I receive. So now I have a control over the data that I get. And so then the interesting question is, so what controls should I make? What kind of data should I basically look for? And this field of agents that make actions to influence their own future. In machine learning literature, the biggest this topic is called reinforcement learning, and there's a whole theory about how to learn actions. And the idea there is that if you build a model, a generative model, so you can run this forward in time. Then you end up in a state, and you can assign values to the state. Basically, you're saying there are certain states where I will be that I value higher than other states. You can call those value functions or reward functions, or the inverse of it, cost functions. And then basically you calculate backwards and say, what action do I have to make in order to maximize my expected rewards or to maximize my expected value in the future? So that's a good approach. But what we want to do in this class is to show that you don't really need this new concept of reward functions. You can actually do everything with the tools that we have talked about, just inference in probabilistic models. What you can do if you have a generative model and you run that forward in time, you can actually quantitatively describe the value of these future observations that you predict by setting up an extra prior on these future observations. I do that in the class, let's say, where do I do that? Here. So we assume we have this generative model. I am at a particular time t, and I run this forward. I just simulate this forward, right? Think of this as I'm trying to cross the street, and I see cars on the street. I want to calculate if this car is going to hit me in the future if I cross the street, right? So I run in my mind this signal forward in time. So the signal consists of actions that I can take, actions that how they influence the dynamics of the world, S of t, and how that relates to observations, x of t, that I will make. And this is, I run this from t to t plus capital T, that means to the future, because I'm running this at time small t. So now I can generate basically predictions for future observations. And I'm gonna sort of ascribe value to those future observations by adding to my model a prior, right? If that would be a Gaussian and this, let's say this predicted future would be in the tails of that Gaussian, well, that's not what I want. I want my future observations to be where the bulk of this goal prior is. And now we can do the same thing. We can basically run this model forward at a time t for a particular choice or for various choices of u of k, of the action that I make at time t, and compare then the predicted observations with the prior, and basically do inference in this model and infer what is the action that I have to make now in order to get observations in the future that match my goal prior, let's say as clean as possible, right? So in this formulation, as you can see, this idea of making actions to get to a certain, to accomplish a certain goal is within this framework of just having a probabilistic model and doing inference in the model, and there is nothing else to it in a certain sense. You can make vector graphs of that, and you can just do inference with message passing. That's certainly possible. You don't have to do it with a vector graph. You can do it with other ways. It turns out if you do this in a Bayesian way, like we do here, then the actions that you choose they have a very interesting property. That is, there is a very naturally balance between what we call exploration and exploitation. If your model is a very good description of the world, you can make accurate predictions, and then you should choose actions that actually make your prediction come true, or let's say that lead to where you have your prior. So we call that goal-directed actions or goal-directed behavior. On the other hand, if your model is not yet very good, you can make predictions, but those predictions are way off. So then you need to actually collect data to learn your model of how the world behaves. We call this explorative actions. So your actions then are basically aimed at, let's try to get the data that I need to train this model, to get most information gain about this model, explorative actions. If you do it in this way, so if you set it up in a Bayesian way, then it turns out that this balance is very nicely done. For instance, if you learn how to ride a bike, and the actions that you make, and you start to fall, the actions that you make in the beginning are explorative, information seeking. You want to learn the dynamics of well, what it entails to ride a bike and how the bike responds if you turn your steering wheel and so forth. Once you have learned that model well, your actions are exploitative, then they will actually keep you upright on the bike. And the same thing happens if you want to cross that street. I can actually simulate my model forward in time, and if I then calculate that the car will hit me, then I'm not going to cross the street. And if I calculate the car will not hit me, I'm going to cross the street. But I can also calculate that it's these probabilities are, let's say, too close to call. I need more information. I can also decide I'm not going to walk yet. I'm going to keep looking, get more information. So then I make an action that is explorative, get more information, rather than making my decision, am I going to cross yet or not? So that's really this lesson. The big thing here is that agents that are intelligent in the sense that they act with the goal of what we could interpret as purposeful behavior. I'm thinking here of robots, self-driving cars, that kind of thing. all that stuff sort of fits in this Bayesian framework of what we have done in this class. So there's no really additional tools beyond probability theory is necessary. So with that, I'd like to give it to you and let you ask questions about this class. You can open up your mic or put it in the chat, whatever you want to do. Okay, so there is a question. The question is, it's still a bit unclear to me. What variables distributions are updated and which ones remain the same when we're doing online active inference? When we do online active inference, the idea is you basically you're in a dynamic world, right? So in the beginning of this class, I tried to explain, and also based on a theoretical paper earlier on, 1970s, that if you want to control the world, you really must build a model of the world. So inside an active inference agent, you basically have a model of how the world, let's say, generates observations that you make from actions that you make, right? So inside, here's the agent, there is a model from an action to how the dynamics of the world is, and I describe that here with state variables that may be a large vector, and then how these states of the world lead to observations that I call in my agent X. So this model may have parameters. So those parameters I'm not going to update, let's say every millisecond, right? So that's very slow. But I need to update the world, then I need to update the states S here. Because I want to estimate the state of the world, and I need to run actually so the world, me in the world, forward in time and get to a particular. So I want to generate what kind of observations am I going to make, let's say 10 seconds from now, or 5 seconds from now. So S and X are going to be updated as if you're just running a dynamical system forward. I'm not sure if that answers the question. Maybe if I can also show it in this vectograph. So this is the state really of your model at time after you make the observation at time t. So you've just sent out an action to the world, A of t. What we do, by the way, is, let's say inside the agent, I call actions, I call them controls U of t, and as they are, but that's still, let's say, a variable in my model. What's actually happening in the world, I call actions. So actions A of t are variables that are in the world. Controls is my model of actions. In the same way, let's say stuff that's happening in the world, the observations, I call them Y of t, and inside my model, I call them X of t. But here I just made an action, went through the world, and I make an observation X of t. Now, at this point, I need to come up with what is going to be my action at t plus 1. That means I need to come up with a posterior distribution for this, for U of t plus 1. And so what we do is, well, I basically run my messages right down here, forward, up from X of t into this direction here. And to this direction here. So I'm getting here basically an update of the state at time t, given all the observations x of t. I'm also going to run for a particular set sequence of actions that I draw from all possible, from let's say a set of action sequences. I'm gonna run this and this and this, and then also backwards to here. These red boxes are my priors. They're not yet observed, but it may be a Gaussian or maybe another distribution. That's where I want to end up. I can run this model forward in time for given actions and make predictions. So let's say predictions for x of t plus t, but I match them to this prior. Eventually, I'm going to send messages backwards, and so I'm going to get message here backward. That message is basically also an estimate for s of t, just like this one, but now based on the future. That hasn't happened yet, but basically this is the s of t where you want to end up if you want to make, let's say, this, if you want to fulfill the expectations that you have about your future observations. So this s of t is where I am now based on the past, and this s of t, this let's say integrating out everything in this box, is where I want to go. And so then I can infer this action u of t, because now I know where I am and where I want to be. So then I make the next step. And so at every point in time, we update states of the world, we update future predictions of the world, and we do that for, let's say, if we test that for different choices in action sequences. Does that help a bit? Okay, super. Anybody else questions?
I have a question that's a bit maybe beyond the scope of this lecture, but I'm very curious how neural networks are related to this active inference agent model.
Okay, so do you mean artificial neural networks or biological neural networks?
Well, to be honest, I don't know, but I know that there exist neural networks and that they also try to mimic the biological agent, like the free energy minimization. So I was just curious, how is that linked with this theory?
Yeah. So, I mean, first, let's say about artificial neural networks, deep neural networks. In a way, you can just take this theory as I told you, right? What you need is you need to have a model, a model of a dynamical model. You need to run that forward in time, and you set priors on it, and then you need to run backwards. You can use deep neural networks for that. You can use an artificial neural networks as your dynamical system. It would help. No, it actually is necessary that it is a probabilistic deep neural network, right? So let's say the majority of deep neural networks, let's say the artificial neural network literature, doesn't have a Bayesian formulation, is not a probabilistic model. But there is a subsection of the artificial neural network literature that talks about Bayesian neural networks, and you can use them as your models here. And so what we describe in this lecture is a general framework. I am not saying that this is a Gaussian or this is a gamma distribution. It may be a complete neural network, a Bayesian neural networks, totally fine. Then there is another link, and that is that this theory of our active inference actually comes from, let's say, the theoretical neuroscience. And this is what Magnus is going to talk about more next week on Friday. But yeah, there is indeed the link to biological neural networks. there is and so that's also how I started out. And the leading researcher in this field indeed is Carl Friston. And the idea that biological self-organization, and that includes the brain, is basically governed by free energy minimization. That's called the free energy principle. And active inference is just an instance of the free energy principle, right? So the free energy principle says all biological self-organization is a matter of free energy minimization. And he really means the free energy minimization that we talked about in our variational Bayesian class. So in a sense, he says, yeah, the brain does variational Bayesian reasoning, right? So we are not perfect Bayesian reasoning machines. We are not Mr. Spock, right? We do approximate Bayesian reasoning, because perfect Bayesian reasoning would mean we have to integrate over the state space of all possible states in the world. That's not computationally tractable, but we can do variational Bayesian reasoning. We can do free energy minimization. So active inference is now if you buy into that, then obviously when you want to build an agent like we are, you have to explain it by coming up with a free energy functional and minimize it. And indeed you can come up with a free energy functional for this, right? Because I have just here a generative model, and I extend this generative model with goal priors, but it's still a generative model. Now it is a biased generative model in the sense that it doesn't make just a prediction of how I think how the world will go. It makes also a prediction of where I want to go, but still a generative model. And I can do my inference. I can come up with a free energy functional and then do inference. And so, yeah, there's certainly links to biological networks. That this is a theory of how our brains work, and the links go even further to physics, right? Free energy principle by itself is let's say almost the same as the principle of least action, which is really a foundational idea in physics. So in one sense, Carl Friston says the brain follows the laws of physics. How could it be anything else? But I'd like to leave that for the last lecture. In this lecture, I want to sort of focus on just the idea that I mean, from an engineering perspective, I've tried to sort of promote in this class that lots of engineering tasks, whether we talk about classification or prediction or regression or lots of other tasks, can be phrased as inference, Bayesian inference in a probabilistic model. You set up your model, you collect your data, and now you do inference to solve your task. Whether it's a parameter estimation task, whether it's a prediction task, it's just inference. And in this lecture, we go to agents, and the same thing applies. We can still just set up a probabilistic model, and the task of coming up with actions, right? How to build a self-driving car, how to build robots that do certain things. These problems, inference or actions, can be inferred in these probabilistic models by Bayesian inference. Technically, you will probably do that by free energy minimization, by variational Bayesian inference. And so that's just the engineering of it. And then, let's say next week we make the excursion. We've already talked a little bit about it, but the excursion that yeah, indeed, there is a whole theory in neuroscience that actually says this is really how the brain works. So I think that's interesting as an aside for us, right? Because this is an engineering class, but it's interesting that this whole theory, I mean, we started from engineering, but at the very end, we were met by the neuroscience, right? And so in that sense, it also relates to biological neural networks. As an engineer, you can use artificial neural networks to implement this, of course. I hope that answers your question.
Yes, thank you.
Okay, cool. How does an agent know when to stop? That's a really good question. In a sense that depends. I mean, yeah, it depends a bit on the application, right? I mean, if you are, let's say, if you are an engineer, you build an agent that needs to park a car at a location, and you measure that you have reached the location, then you stop. In the real world, let's say the world just always goes on, so you never stop in a certain sense. You just keep chasing new goals, right? It also depends on, let's say for ourselves, if I want to park my car and then I can say, okay, task accomplished, so it stops. But I also have higher goals. I want to. I'm also in the business of just surviving, so my life goes on. So there are sort of higher goals, right? So I don't stop living. But generally, as an engineer, I think you should just try to specify your goal in terms of a probability distribution over future observations. What is it that you want to see in the future? And if you do that, let's say, and time passes by, and you reach your goals, then you stop, right? I mean, there isn't, in the Bayesian framework, there isn't a stopping criterion, right? There's just inference. So as an engineer, I think you should make that decision. Okay. Feel free to ask more questions. So these are all really good questions. So the question is, can you set the future priors on observation? So the goal of the agent to be uninformative. If so, what is an agent going to do then? Yes, you can. Of course, that's, in a sense, that's the same thing as not setting a goal prior, right? So, but because not setting a goal prior is setting that goal prior just to the value 1 over the entire domain, or constant over the entire domain of all your let's say, if your observation domain, right? So then you don't have, let's say, an external goal. You just have a model of the world, and the agent will make actions to gather information to learn your model. So the actions will be explorative. You will seek data to maximize learning about your model. As I said, this free energy functional breaks down. It's in the optional slides. It breaks down in a component that we call. I can probably go down and show you. You don't really have to. It's an optional slide, so you don't really have to follow this. But there is. Let's say the free energy functional breaks down in something that we call pragmatic cost, goal-directed, and epistemic. Epistemic means information-seeking costs. So if this falls away because you don't have your prior, then you are just basically in the business of trying to find the data to learn your model of how the world behaves. So it's purely epistemic then. Yeah, and Magnus is a teaching assistant in our class who will teach next class, who also has additional comments on the stopping question. So feel free to read that as well. It converges. So the short, I'll read it for you also because it's for the video. The short answer is that an agent never stops. It converges to a goal distribution. You can decide to stop it yourself if you want. Otherwise, the agent is going to keep trying to stick to the goal prior. For instance, you can imagine that a robot is parked somewhere as long as it's there. It doesn't move. However, if you push it somewhere else, the divergence increases and it starts to move back. Yeah, that's a good point. If you, let's say, once your observations match, let's say, your goal distribution, then it naturally stops. Then the action will be stay where you are, right? And as long as that is not the case, if, let's say, where you want to end up doesn't match where you actually are, then there is a prediction error, and you will make actions to minimize the prediction error, or to minimize the expected free energy, as it's called. Very good. The issue, this class about active inference agents is a difficult class. And in all honesty, this is a field that is highly immature and under development. This is or immature, depends, of course. There are a few researchers who know a lot about it, but it's not too many researchers know a lot about it. It's really a field that is under heavy development, and it's only been a few years, 5-6 years, that this kind of techniques, let's say, have draw any attention from engineers, right? And it's been only roughly 10 years since this active inference has been described in the theoretical neuroscience literature, and maybe 5 years since engineers starting to pick up on it. And it's still a very small fraction of engineers, but it's extremely elegant and beautiful, and it fits totally in, let's say, in our Bayesian framework. It's also a growing, let's say, growing field, but it's on the one hand, it's extremely simple because you can say, well, you just have a generative model and you do inference, and you have a goal prior, and that's it. On the other hand, if you think through the complications, then you're going to need a lot of time, much more than this class, to think through all the complications that can arise. One of the complications is you are in a loop, right? In an action perception loop. When I make actions, I change my data. That these observations change my estimate of the state of the world. In biology, that means perception, but it changes what I think about what the state of the world is. That changes my actions, which changes future data. So I'm in a loop, and I'm collecting a data set that I could never collect in anywhere else without me making those actions, right? So I can collect a data set this way that cannot be collected if I weren't in this real-time loop. It also makes it unpredictable, the data that I collect, because I'm not having I don't have a perfect description of the world. There's a lot going on in the world that's not in my brain, that I can't predict. So the data that I collect is unpredictable in a certain sense. I'm trying to make predictions, but there's a lot of uncertainty. And so that, yeah, it's hard to get your head around it, and I understand that. So let's, my expectations in terms of how deep you comprehend this aren't very high. I just hope you appreciate the sort of the elegance of the idea that you don't need an additional engineering tool to make an intelligent agent. Yeah, so I see there's some a little discussion. The question was, how does this method handle sparse rewards? You don't, and Magnus answers, you don't really have reward functions in this framework. You have a goal prior instead, which biases inference. So effectively, the reward maximization problem is bypassed and replaced with an inference problem. Yeah, so some of these things are going to be talked about next week when Magnus will take this more to the neuroscience. In, let's say, the classic formulation of reinforcement learning is that let's say when you drive a car, and so let's say I'm an agent that drives a car, the actions that I can make are I can steer the wheel, and maybe I can press the gas pedal and the braking pedal, right? So that's my action space. The observations that I make are I don't know, going from, let's keep it simple, from some video processing, right, on the roof. So those are my observations. And then once in a while, I'm getting a reward from the environment, right? Once in a while, the environment needs to tell me, oh, you're doing well, or basically if I hit something, you're not doing well, right? So these are called rewards or punishments, right? So once in a while, you want to get performance feedback on how you're doing, and the idea is in reinforcement learning to maximize your future rewards, to maximize, let's say, there's the idea is that you, so in the future, somebody will tell you, oh, you're doing well, or you're not doing well. That could be a human driver, yeah, things well, or a human driver making an intervention, right? That means you're not doing well. You want to, because he's avoiding a collision. And those rewards are sparse, right? You're not going to continually say you're doing well, you're doing well, you're doing well. No, you just let your car drive, and once in a while you make an intervention. So you get only sparse rewards. In the reinforcement literature, these rewards are treated differently from the video processing observations, right? Those are your sensory inputs, your data, and then there is a special class of observations we call rewards, and they're very sparse. In active inference, you don't make that distinction. They're all just observations. So these sparse rewards, performance rewards, are also observations, right? And we also describe them as so they're just a channel of sensory inputs, and we need to build a model for them, and we can set priors on them. So there isn't a special thing for separating, let's say, sparse rewards from video input. They're just different streams of data. That's all. Are there any other questions? Why is it called the free energy principle? Where does the name come from? It comes from physics. In the class on variational Bayes, right? I said we talked about the entropy, maximum entropy method, and then I said, okay, the inverse of the relative entropy, or the negative, is called the free energy, and so we can do Bayesian inference by minimizing the free energy. The term comes from the physics literature. Let's say thermodynamics. Free energy, you can say energy in general is composed of, has a piece that you can use to do work, and a piece that, let's say, are random movements in let's say there's if you look at it kinetically, you have coordinated movements. You can use that to do work. And you have random movements, and that's what we call entropy, right? Disorder. So your energy is your free energy plus your entropy, or free energy is your total energy minus entropy. So that's where it comes from in let's say in the physics world, because it's a term from the statistical physics or thermodynamics, right? Every time you can write a function as an energy minus an entropy, we call it a free energy. It's free in the sense that that's what you can use to do work. For us people, our free energy comes from food and let's say photons, sunlight. That's where we get our energy from. This is the energy we just get for free, and we can use that to do work. And we also generate heat. Right, our temperature is a lot hotter than, let's say, the surroundings, so we emit heat, and that's our entropy. Yeah, that's where it comes from, basically from the physics. There are people that yeah, you can use, let's say, the nomenclature from information theory. And in information theory, you would talk about relative entropy and cross entropy and mutual information, and you can set up the same framework with the same functionals but give it different names. In this class, I use the term free energy because that's what is called in neuroscience, and so yeah, because the theory of Carl Friston, namely that biological self-organization, so everything how brains process information, but actually it extends beyond brains. This is all based on free energy minimization. This is called the free energy principle. That's why it's called the free energy principle. And so that is in a physics principle, if you will. I think the most interesting or an interesting thing is that minimizing free energy, which you can think of as physics, happens to also correspond to Bayesian information processing, right? The handout that I gave you in our the lecture notes, the manual by Ariel Katica, is all about that. It's all about describing physics as an information processing science, right? So there are strong links between information processing and how we describe, let's say, physical laws. Yeah. I hope that helps. So there's another question in the non-Bayesian machine learning. There are recent examples that scaling up the models in terms of the number of parameters in combination with a lot of data leads to quite well-performing models. Can we expect some similar thing for such agents when scaling the number of parameters? Yeah. Yeah. The idea, of course, in let's say deep learning and in the machine learning literature, there's a lot of attention goes to at the moment to building really big models with lots of parameters, not just millions, but tens of millions, hundreds of millions parameters, throwing in a lot of data and learning and then getting a good performance. This is great. There's also a bit of a literature that says, well, maybe these huge neural networks with all these parameters are kind of building lookup tables. Are they really learning, or are they just storing the data, right? You have almost, if you have more parameters than you have data, you can question, are you still building a model? In the sense that a model, I think, is something that summarizes the data. If your summary is bigger than your data set, then it's no longer really a model, right? So there's a lot of interesting questions there. But generally speaking, let's say what Bayesian machine learning adds to this equation or to these issues is that you have built in the evidence, Bayesian evidence. We always talk here about let's use inference to get a posterior for the parameters. That's true. But there is a second term that Bayesian inference gives you, model evidence. And this scores how good your model is. In the non-Bayesian literature, if you do parameter estimation, you get a set of parameters and you can test them on data, on a validation set or test set. This is all fantastic. But you don't have really, let's say, a fundamental performance measure. And in this framework, there's a fundamental performance measure of how well performing the model is. The other thing that's just a sort of a side remark to what you're saying here, that in engineering, it's true that if we get huge databases and build huge models, you can get good performance. But that's not how we work in, let's say, how we learn, right? We make our actions to basically learn, to get the most informative data, to learn from small data sets. I cannot afford to wait for big databases to come my way. We make actions. I mean, when you actually, let's say, your perception of what you see, is really just based on very little information from the outside world. Most of it actually is your prediction, and then you target. You go with your eyes to certain spots to pick up the information that you need to fill in the pieces. So we very much are involved in actively selecting the most informative small data sets. So in that sense, that the current trend in machine learning to go to bigger data, bigger machine learning is not in line with how, let's say, biological intelligence works, which is not to say that it can't be very useful for engineering. But it's not how biological intelligence systems work. Yeah, that's basically the comment I want to give on what about big models and lots of parameters. Anything else? And feel free to also, if you read this, if you read through the lecture notes and some new questions arise, feel free to post them in Piazza. It doesn't have to be something for the exam. It could be just a general question like we've talked about now. Something, about, let's say, about scaling up, or how it relates to other frameworks. It could be any question. So just feel free to post your questions in Piazza as well. Okay, then I think we're busy about 50 minutes now, so maybe it's a good time then to close the lecture. Well, thanks a lot for your really interesting questions. And then, yeah, I wish you a great weekend, and we'll see you next week. Okay, bye-bye, and thanks for attending.